In this example, you're again being asked to draw the products of the following acid-base reaction below, and then you're going to label each compound as the acid, the base, the conjugate acid, or the conjugate base, and then you're going to determine the direction of the equilibrium. All right. So just like the last two examples, let's identify what is going to act as the base here. So in the last two examples, the negative charge was very clear. It was written out. In this example, we see that we have sodium hydroxide. So sometimes you're going to see things written like this with their cation there. So it's important that you recognize what that means is you're going to be using hydroxide. So hydroxide is going to be our base here. So we're going to go ahead and label that as our base, which means in this species is going to be our acid. And we have to figure out which protons are more acidic on there. So again, if you're using the pKa method, you'll kind of recognize that this thiol here, that has a pK of approximately 10 to 11, somewhere in there. This alcohol has a pK of about 18. And then these two carbons here, they probably have a pK somewhere around 50 or so, probably a little less. But if you're using the pKa method, that'll let you know that, hey, the lower the pKa, the more acidic, which means this proton right here is the most acidic one. That's the one that the base is going to remove. That's using the pKa method. Let me get these out of my way. All right, but again, let's say you don't know the pKa. If you don't know the pKa, you can still figure out which protons are more acidic by looking at the conjugate bases. So let's remove the proton on the sulfur. So I'm going to put negative charge there. That's one conjugate base. Let's remove the proton on the carbons. So there's a negative charge there. And we'll do the other one for the sake of argument. So negative charge there. And then we'll remove it from the oxygen. So a negative charge on the oxygen. And again, we're just trying to figure out which of these conjugate bases, 1, 2, 3, or 4, which one's most stable. The one that's most stable is the one that's most readily going to form, which means it's going to be that proton that gets removed to form it. Strength of an acid, directly proportional to the stability of the conjugate base. So when we look at these things, we're going to compare negative charge on sulfur, carbon, carbon, and oxygen. And we're just trying to figure out where's that negative charge most stable. Well, we know oxygen's more electronegative than carbon, so it's not going to form on the carbon. So that's not going to be the most stable conjugate base, and that's not going to be the most stable conjugate base. So it's either going to be the negative charge on the oxygen or the sulfur. Now, oxygen is probably a little bit more electronegative than sulfur, so you might think oxygen's going to handle the negative charge better. But we have to keep in mind there are other things that stabilize negative charge. Things like induction, electronegativity, resonance, hybridization, atom size is also a factor. So here, sulfur is larger than oxygen. So I'm going to kind of depict that here. So sulfur has one extra electron. So it's 1 unit of negative charge. Oxygen, being smaller, has the same amount of negative charge, but it exists in a much smaller space. So there's more electron repulsion in the oxygen, which is going to be destabilizing, which means the sulfur with negative charge is more stable. And if it's more stable, that means the proton is going to get removed from the sulfur to form a more stable conjugate base. So that just tells us the same thing the pKa told us. It tells us that the base is going to remove the proton from the sulfur. And that means we're going to get this conjugate base plus the conjugate acid of hydroxide, which is just water. Okay, so here's our conjugate base. Here is our conjugate acid. So we have everything labeled, we have the products there, now we need to figure out the direction of the equilibrium. And again, we can use the pKa method, and we can realize that, this acid has a pKa of around 10 to 11. And the acid on the right side, water, has a pKa of around 16. Well, the equilibrium is going to go away from the stronger acid. So that means the equilibrium is going to go towards the conjugate base and water. That's the pK method. The other way is we'll just compare the stability of the two bases. And what we're comparing here is hydroxide versus this base. Which one's more stable? The one that's more stable is the one that's going to dominate here. So again, we're just asking ourselves, which negative charge is more stable? Is it more stable on oxygen, or is it more stable on sulfur? And we already evaluated this. Sulfur is larger and it handles the negative charge better because it has more space. There's less electron repulsion. It's less reactive. That means this is a more stable conjugate base, which means the equilibrium always goes towards the more stable conjugate base. It goes away from the stronger acid and towards the more stable conjugate base.